this is from the forecaster point of view. I talked about the models. Now I will discuss about some of the reanalysis that we in-house generating, that is called IMDAA. You can see this presentation as kind of an advertisement to our reanalysis product as well. With that, I will talk about the moist dynamics in the reanalysis. So this work is a recent work that we have done and published in recent in a journal. So this is actually a revisit of earlier work by Prasanna and Annamala in 2012, where they have studied the moist dynamics of extended monsoon breaks, especially the breaks or Indian Southeast Asia. There, the essence of that paper is that the breaks that are occurring over central India or the core monsoon zone are actually manifestation of both the inherent monsoon intraseasonal oscillations as well as the remote responses from the ENSO. So slowly varying boundary conditions will also act in maintaining this extended monsoon breaks. That's what their essence of the paper. So I thought that they have done with the ERA interim data. So we just want to see how good our reanalysis, that is a regional reanalysis, is representing this kind of a moist dynamics or breaks. And of course, I have considered active conditions also. So it is kind of a revisit of the paper. So before going into the talk, I just want to give you a couple of points about the IMDAA reanalysis. It is a Indian monsoon data assimilation and analysis. It's called IMDAA. It is a very high resolution, 12-kilometer reanalysis. And it is regional reanalysis. You can see the region. It covers most of the Indian monsoon domain. We had from 1979, that is a satellite era, from the satellite era to 2020, we had the data set. So it is pretty good data set, 42 years. So if any researcher or student who is working on AML or training your models, I think this could be a very good add-on for your research. With that, so what I have done is that computed the active and break cycles, identified the active and break cycles in the IMDAA reanalysis. So just maybe with the figure, this is the histogram of the events that identified based on the IMDAA rainfall. If you look at the left panel, the break histogram and the active histogram, the events I have categorized as 3, 4, 5, and 6, and beyond 7. So these are the number of events that I have taken. And if you see, these events are characterized or computed based on the standard rainfall anomalies by the well-known definition of Rajavan et al. In 2006. So we adapted the same methodology to find out these events. And when you look at the events, this is the histogram that follows in different kinds of data sets with the IMD 0.25 degree rainfall, TRMM, and then IMDAA and ERA5. You have this parabolic distribution for the breaks, and you have the active is exponentially decreasing kind of event. So basically what happens is that Indian monsoon, if you see, the droughts and floods are not symmetric, asymmetry in the floods, because we have more droughts than the flood years. So that's how you can see beyond 7 days, you can see again the incremental changes in the increasing events above some certain threshold. So what I have done, I have not, this spectrum, I have not done moist dynamics for all the events. I've combined, I've taken the short events as it is, and then 4 and 5 I have combined and call it as a medium, and then 6 and beyond, I take it as a prolonged break. You may be questioning why this kind of a segregation. What I have done is that before going into the analysis, I just made a spatial map of these rainfall anomalies and their spatial evolution, the oscillatory behavior. Then what I saw is that the spatial anomalies of medium 4 and 5 days, the evolution of the spatial anomalies are more or less similar. So I have combined this 4 and 5, I call it as a medium. Similarly for the prolonged. So over the central India, if the spatial anomalies, like I'm talking about the spatial anomalies, if I do the evolution of these anomalies, rainfall anomalies over the central India, for the break and for the active, the solid is, they are messed up. It's like a spaghetti plots, but you see the solid line is for the IMDAA and the dashed line is for the observations. It's IMD, sorry, I wrote here of it. But then if you see the observation, that is a dashed line, just concentrate on the red line. The red line is going, and then around 0, that is a near normal condition, monsoon condition. It is stalling around the near normal even after 10 days. Once the prolonged break has occurred over central India, and then it goes back to the another convective cycle. But the prolonger breaks are just stalling around the zero, near normal, and they are not going into the active monsoon condition again in the observations. But if you look at the IMDA, same feature you can see, it is going up, but then it is going back to the, again, the break phase. I mean, like the oscillatory behavior of ISO in IMDA is slightly weaker, I can say here. The other important point can be noted here is the short breaks. The blue color solid line, if you look at the observation, the blue color solid line, there is a sharp decrease in the observations. But the dashed line, the solid, if you see, the 3-day break events are very smooth in IMDA. Maybe because of, maybe I can speculate that could be the data assimilation that we are using here, that reanalysis or the gridded mean products here that compared to the observation, or the data assimilation techniques that we are using, maybe this causing this kind of a smooth kind of a transition in the rainfall. Similarly for the active condition. So by identifying these active and break spells, I'm segregating into different events. What I have computed is that before going in, I just want to see the mean state and bias in the IMDA data. I don't know how this. So if you look at the mean state and bias, this is the TRMM observations from 1998 to 2018. The same data, subset of data I have taken from the IMDA. If you look at the mean state, most of the heat sources, or you can say the principal rainfall maxima along the Arakan coast, west coast, and the foothills of Himalayas, central India, these equatorial regions are well represented in IMDA as well. But if you look at the daily variance, raw daily variance, without not the filtered, just the daily variance, the equatorial regions in IMDA is, they're not good as the observations. You can see this. A lot of differences between the daily variance. And again, if you look at the bias between the observations and the rainfall, in the rainfall in IMDA, you have a very wet bias over land in IMDA. Generally, the rain, you can see that unlike any reanalysis product, which is dry land regions, but in IMDA you have a wet bias over land and then kind of a wet bias over western equatorial Indian Ocean. And then the dry bias are seen, there is a dipole kind of a structure in the east-west, the dry and wet here. So probably equatorial wave dynamics may be affecting here with this bias structure. So when I look at the vertical structure over central India, which is my main study region, you can see that the wet bias that we have seen in the rainfall could be because of the moisture that was central India. If you concentrate on the purple curve, where you have a very strong moist conditions, the bias is very strong here. And then, warm and bias, or warm and moist conditions are prevailing over central India when you are area averaging. So that could be a reason, maybe you can attribute to that most wet biases that we are seeing over central Indian region. And again, the essence of this plot is if you look at most of the differences in temperature and moisture, or the associated quantities like dry static energy and moist static energy, or the vertical gradient of moist static energy, most of the things are happening in the boundary layer. The differences between the two reanalysis, IMDA and ERA5, if you see, the large differences are seen below the boundary layer. So again, like I said in my previous talk, last couple of days before, the model that we are using, the dynamical code that we are using for generating this reanalysis, having a boundary layer problem. Either it could be a very warm or it's dry. So that is reflecting in our reanalysis product as well. You can see this. Another important thing is that the upper tropospheric peak in the vertical velocity. The vertical velocity is also having an issue. In my earlier work, we have shown that the main culprits of moist dynamics in model is omega and moisture. With that, if I have compared the moist static energy budget, I don't want to go into the details, but I just want to highlight some points in the short break. Sorry for that. This is because of this version change. This the letters are messed up, but then when you look at these different terms of the moist static energy, different legends, different terms are different in different colors. You look at the red one, that is the horizontal advection of moist static energy, or the moisture. If you see, they are in hand with the precipitation. They're going with it. There is no lead lag kind of a thing. That's especially for the short breaks. The prolonged, you can see some kind of a leading nature between the rainfall and convergence, horizontal advection of moisture. But then in the short breaks, it is not there. Probably I can speculate this could be because of the fast convective adjustment, because the breaks are very short. It's not allowing energy atmosphere to slowly evolve the MSE. So the charging and discharging are happening at the same time. So that could be one reason the short is having a one-to-one correspondence with the rainfall compared to the prolonged. And the other important aspect we have found is that the highest residual, the residual magnitudes are too high. It's matching with the, although they are in phase with the leading term, that is the moisture, horizontal advection of moisture, but still the residuals are very large. Now we are planning to do this kind of a budget with the model time step in the UM. Let us see whether it is closing or not. This reanalysis are not able to do that. Let's find out what is happening in the UM model. And just want to find out how the strength of the convection in gross moisture stability. This is one term where the export and import of moisture into the column. We just want to see how the GMS is representing. Again, GMS is not also performing well as because the other MSC quantities are not good. Some places it is performing well, some it is not. But still, if you look at the short, that's a blue color one, always every time it is a positive GMS. Positive means it's the export of moisture is happening in the break. It is not going into the other, active condition. The oscillatory behavior is not seen at all. But in the prolonged condition, you can see that you can see some kind of oscillatory behavior. You can see it here. One more minute. The most what I found is that the main culprit would be the vertical velocity. If you look at the IMDAA and ERA 5, the distribution of vertical distribution of moisture and vertical velocity, short, medium, and extended break. Similarly, the same exercise for the ERA 5. If you see, most of the panels look similar, not much variation, but the major difference you can see is vertical velocity. The IMDAA vertical velocity, ERA has very dry kind of a thing, or the descent is seen 10 days before. That means the the dryness conditions are happening 10-15 days before, but in our IMDAA, that kind of a structure we haven't seen. A lot of regions, the ascents and a lot of noise and continuous ascent and descent regions are seen in the ERA 5. Although this is regional reanalysis, we don't know how to, we can't find the source of the term because from the earlier work, the sources are coming from all the way from the West Africa, which we can't see in the regional reanalysis, but we are speculating that this could be because of dry air. This is schematic, and you can find these details in the paper that I have mentioned here. With that, I'll stop here. Thank you.
Yeah, questions? Thanks, Mohan.
In your bias plot, I could see most, the maximum bias was near the windward side of the orographical regions. But you have shown for the central India part, that's okay. But could you please comment on, is it because of that the other foothills of the Himalaya, you could see more bias as compared to the central Indian region? Is it because of the existing error in the spectral models, or is it some other mechanisms?
Because this reanalysis product is basically the analysis one. That comes from the data assimilation technique that you give. Most of these Himalayan regions don't have this. This is a problem for even the satellites, because getting the proper representation of rainfall or the pocket over the orographic regions is always a big problem. So which is obvious with then this IMDAA also showing the same thing. In a way, we are consistent with showing that, but then still this is a big problem in orographic perspective.
Other questions? Mohan, actually, you had this nice moist static energy budget lead lag. So I was just wondering, for short versus prolonged breaks, the phase association between moisture and precipitation changes. And these plots are averaged across central Indian region. So the short, do we know spatial structure of short breaks versus prolonged ones?
I haven't put here, but then the major difference we have seen is that for the short breaks, 1 week before, the rainfall anomalies that are propagating towards BSS, that's a northward propagating anomaly. So Bay of Bengal is getting dry first, and then that is propagating towards northwest direction towards central India. That is like a synoptic systems going on the 3-day. But in the prolonged break, it is, those are coming from the west, Arabian Sea and all those things. Even the Bay of Bengal is dry. But we can see that the Hadley cell is, the local Hadley cell, the equatorial Indian Ocean is very dry, or the descent is seen in the prolonged break, which is not in short breaks.
Right.
So it is only the localized phenomena for the shorts rather than the. Another important here, I want to see the green curve, which is the omega dou H by dou P or dou M by dou P, the vertical advection of moisture, which should be actually in phase with the rainfall, hand to hand. But you can see here it's showing sometimes some kind of a leading nature, which is also just because of the omega that IMDAA is having a error. So we're not able to get one-to-one correspondence between the omega versus the rainfall.
Right. You mean omega dou Q dou P, I guess.
Yeah, omega dou
or dou M dou P.
Dou M
Because
by
M, I guess, could play more funnier, I guess,
maybe.
based on Eric's talk earlier. Yeah. Thanks. Are there any other questions? Maybe if not, then let's thank Mohan for a talk.